Welcome to the third video in a series of 8 about polar graphing, limacons. This image should remind us that for any radian measure terminating at point A on the unit circle, the cosine is the x-coordinate of that point, and the sine is the y-coordinate of that point. So as when theta reaches pi over 2, we can see that the sine value is 1 and the cosine value is 0. When theta reaches pi radians, we can see that the cosine value is negative 1 and the sine value is 0. When the radian measure reaches 3 pi over 2, we can see that the cosine value is 0 and that the sine value is negative 1. And when our radian reaches 2 pi, which is coterminal with 0, we can see that the cosine value is 1 and the sine value is 0. Here's a still of that same image, and here are the 8 very important values that we just mentioned in the last clip. So with that in mind, let's take a look at our first problem. We're going to look at a shape today called a limacon. Here's an equation of one. The question I always start with when graphing any polar function is, how are changes in theta going to affect the variable r? And what I like to do is I like to ask myself this question quadrant by quadrant. So as theta goes from 0 to pi over 2, in other words quadrant 1, I wonder what's happening to r values there. Likewise, quadrant 2, 3, and 4. And if I can answer this question, how r is changing in each of these quadrants, I'll have a perfect picture of what this graph looks like. Now to know that, it would help to know the value of r at each of these so-called quadrantal angles, the angles that aren't in quadrants. So a good start is to plug these 5 values of theta into your equation to find the values of r. Now if it's been a while since you've done trigonometry like this, let's just look at one in particular. Taking this one here, figuring out the sine of 3 pi over 2 as the y-coordinate on the unit circle, that would be negative 1. And then some simple algebra shows that I have an r value of 1 when theta is 3 pi over 2. So if I do all 5 of these problems that way, I'll eventually get these answers. And the algebra is not shown here, and I don't want to focus on that now. But it's something that you could easily do. Now, what have I found? Back to my question on the right side of your screen, how do changes in theta affect r? Well, if we want to know in quadrant 1 what's happening to r, we simply have to look over here and say, okay, as theta goes from 0 to pi over 2, r is going from 3 to 5. So I'll write 3 to 5 here to symbolize that. Now let me be a little more explicit about what I mean by that. This is not something you would actually do, but notice that I've picked a bunch of theta values here from 0 to pi over 2 being about 1.57 radians. And I've computed on a calculator r for each and every one of these choices of theta. And notice, as theta goes from 0 to pi over 2, r does in fact take on all the values from 3 through 5. So for the rest of this video series, when you see me write 3 arrow 5, that's the kind of thing I'm talking about. All right, let's continue. Quadrant 2, as theta goes from pi over 2 to pi, r goes from 5 to 3. I can symbolize that this way. In quadrant 3, r is going from 3 to 1. I'll make a note of that here. And in quadrant 4, as theta goes from 3 pi over 2 to 2 pi, r is going from 1 to 3, which I will denote here. Okay, so now I've answered my first major question. What's happening to r in each quadrant? In other words, how are these changes in theta changing r? Now I want to know, how are these going to affect the actual graph?
Watch as theta sweeps through quadrant 1. R is going to go from 3 to 5. Then in quadrant 2, R will go from 5 to 3. Quadrant 3, R goes from 3 to 1. And quadrant 4, R goes from 1 to 3. And if we let theta go past 2 pi, we start to retrace over some of the same points we've already been.
Let's take a look at another one. Here's our next equation. We want to ask ourselves the same question. How do changes in r affect the changes in theta? Again, the best way to do that is to look at quadrant 1, 2, 3, and 4 and see what's happening to r values in each case. The best way to do that is to know the value of r at all the quadrantal angles. Again, that means angles that aren't in a quadrant. So I'm going to plug in these 5 values into my equation to find the value of r. I won't show the trigonometric algebra here, but if you do the work, you will get these values. If you're more comfortable pausing the video or rewinding and doing the math for yourself, feel free, but I don't want to lose the bigger picture here. So just like before, in quadrant 1, we can say that as theta goes from 0 to pi over 2, r is going from 0 to 3. I'll put that here. In quadrant 2, r goes from 3 to 6. In quadrant 3, as theta goes from pi to 3 pi over 2, r shrinks back down from 6 to 3. And in quadrant 4, r shrinks further, going from 3 to 0. So this table shows my analysis of what's happening to r in each quadrant. And of course the question is, how do these changes in r affect the graph? Let's take a look at that.
Watch as theta sweeps through quadrant 1. R will go from 0 to 3. Then, as theta sweeps through quadrant 2, r will go from 3 to 6. Then, through quadrant 3, r goes from 6 to 3. And finally, in quadrant 4, r goes from 3 back to 0 where we started. And notice if we go beyond quadrant 4, in other words, allow theta to go beyond 2 pi, we again start tracing over some of the points we've already plotted.
Here's our third example. Once again, I want to track this through the quadrants by finding the quadrantal values and asking what's happening in each quadrant. So I've plugged my 5 quadrantal angles into the function, do some trigonometric algebra, not shown here, and you can go through the same analysis of what's happening to r in each of the 4 quadrants. Nothing terribly new there compared to the last 2 problems. But again, question being, how is that going to affect the shape of the graph? That's the real challenge here.
First, watch as theta sweeps through quadrant 1. R will go from 7 to 2. Then, as theta goes from 90 to 180, or through quadrant 2, something unusual is going to happen here. Notice in the table, it shows that r is going to go from 2 to -3. Well, if something is going to go from 2 to -3, it has to go through 0. So watch what happens in quadrant 2. Here's r going from 2 to 0. And then, for the rest of quadrant 2, r goes from 0 to -3. Then, as we go through quadrant 3, notice in the table in the upper right corner of your screen, r is to go from -3 back to 2. Well, again, it's going to have to go through 0 there. Here's r going from -3 to 0. And that's part of quadrant 2. But as we complete our sweep through, quadrant 3, notice that r is going to go from 0 back to +2. And finally, as we sweep through quadrant 4, r will go from 2 back to 7, where we started.
Now I'm done with my 3 examples, but I have a lot more to say in this video. The first thing to think about is that in every problem I've done so far, I've looked at the 4 quadrants. In other words, I've allowed theta to go from 0 to 2 pi, and I've claimed that that's enough. I haven't looked at any negative theta values. I haven't looked at any theta values higher than 2 pi, essentially. The question is, are we always going to be okay just picking theta values from 0 to 2 pi? Is it safe to assume that we don't have to look beyond that? Well, yes and no. To illustrate the concept I'm getting at here, I want to take a problem we did previously in this video and pick a random point on our graph. This is a limacon that we saw earlier. And what's worth noting here is that this point is not particularly relevant to the graph that we did earlier, but it is on the graph. Now, this portion of the video is not telling you how to do anything. This is a concept moment in this video. What I did is I picked a common value for theta, just sort of out of all the lists I could have picked, I just sort of randomly picked pi/6. It's one of those common values, and I plugged it in. And since the sine of pi/6 is a half, as your previous trigonometry problems would tell you, I find that when theta is pi/6 or 30 degrees, I have an r value of 4. So this dot on my graph is 4 spaces from the origin and has a standard angle of 30 degrees or pi/6. No mystery there, hopefully. But now to the question, what about negative theta values? Do we have to consider them? Well, I picked a negative theta value here. And it turns out the reason I picked -11 pi/6 is it's coterminal with pi/6. And so the sine is a half just like before, and with a different value of theta here, you'll notice that I got the same r value. But since those theta values are coterminal, that negative theta value would also lead me to that same dot that you see on my graph. And now to the question, do I have to look beyond 2 pi? Well, I picked something a little bit larger than 2 pi to illustrate the point. Now 13 pi over 6 happens to also be coterminal with pi over 6 and negative 11 pi over 6. They all line up at 30 degrees essentially, and so it's not surprising that I would get the same R value there. So this point right here, it turns out, has multiple representations, in fact infinitely many representations, using all kinds of different theta values that are coterminal with pi over 6 or 30. Here's the idea. Most of the time, you can just consider angles from 0 to 2 pi, but there are some rare cases where we'll see later where that is not the case, where we have to think of theta going beyond 2 pi and also have to think of theta being negative. But in 99% of problems that involve trigonometric functions, such as sine and cosine, which are the focus of this video, even though you're technically supposed to consider all theta values between negative infinity and infinity, if we were to do that in most cases, we would just keep wrapping around the same graph, finding the same points. And just because a point appears infinitely many times on a graph as we allow theta to sweep through different values, doesn't mean that that point is any more than just on the graph. Anyways, that's a little strange, and if you got lost in the logic there, or I didn't quite say it right, here's the bottom line. Most of the time, if there's a sine or a theta, or a sine or a cosine in the problem, you're good enough just going from 0 to 2 pi and calling it a day. Now let me summarize some things that I've noticed about limacons over the decades of graphing polar equations. I've noticed a lot of things, and I want to share some of the things I've noticed with you. I wouldn't expect you as a beginner or even an intermediate student in this subject to know anything that I'm about to say. I'm not telling you how to solve problems, and I'm just giving you some observations. Okay, in general, limacons are equations that are in either of these two formats, as our three examples have been. Now it turns out there's some things I've noticed. You're not expected to know this. I'm just pointing out some observations. I've noticed over the years, decades, that if A is smaller than B, we get kind of a pretzel shape. But if A is larger than B, we get a little bit of a dimple in our limacon. By the way, side note, I looked up limacon in a Latin translation, and I don't know if this is true, but apparently it comes from the word snail. And I guess somebody thought that this shape looked like a snail enough to call it a limacon. So if A is larger than B, we get a little dimple, as you can see there. And if A and B are the same, we get sort of a pointy dimple. In fact, when A and B are the same number, we call this limacon also a cardioid. And that comes from the fact that it's kind of heart-shaped, I guess you could say. Now let's analyze this A is smaller than B case a little bit further. Remember, I'm just sharing my decades-long observations. None of this is stuff you will ever be expected to know, as far as I know. If A is smaller than B, we get a pretzel, but that pretzel could be facing up or left or right as well as down. So essentially it's going to be facing one of these four directions. Now what determines that? Well, I've noticed that if I have a sign with either a plus or a minus in it, I'm going to get an up or down facing pretzel. But if I have a cosine with a plus or minus in it, I'm going to get a sideways facing pretzel. Let's examine what happens when A is larger than B. When A is larger than B, we get this dimple in our limacon. But again, that dimple could be facing down, up, left, or right. One of the things I've noticed, and you are by no means expected to know, is that I get a downward or upward facing dimple for sine problems, and a left or right facing dimple for cosine problems. And again, whether there's a plus or minus also plays into that as well. What about when A and B are the same? Well, when A and B are the same, we get a cardioid-shaped limacon. Again, the little pointy part of the heart could be on the bottom, the top, the left, or the right. And that depends on the equation, of course, and whether we have sine or cosine. Now, here notice I used the same letter twice. I didn't call it A or B, I just called them both K. Algebra rule, if we use the same letter twice in an equation, that represents that there's the same number in both places. So, if I have a sine with a plus or a minus in it, I'll have either a down or up heart, and if I have a cosine, I'll have a left or a right heart. Now I've noticed things even further than that. And again, I'm just sharing observations with you. I'm not giving you any strategies here. I've gone as far as to look into things like this. Let's take the one specific case where A is smaller than B, and I have a sine in my limacon equation, and I have a plus. Now that's the one that would lead us to sort of a downward-facing pretzel, if I could call it that. I could tell you tons of formulas and things about this. For example, this point here, this y-intercept is A plus B, and this y-intercept is B minus A. And these two x-intercepts are both A and negative A. Now, if, and I suspect this may be the case, if you've ever been taught graphing and somebody taught you to graph by giving you equations with A's and B's in them and showing you where that impacted the graph, I have to give my personal opinion here that that's not the best approach to learning how to graph things. Now, when students use formulas like this, they essentially just become the app. They become the graphing calculator. Well, if all we want out of this problem is a right answer, you don't need any of this. All you need is your cell phone and an app like Desmos or maybe your Texas Instruments graphing calculator. None of the analysis of having theta sweep through the quadrants is relevant if you have technology. The purpose of graphing in polar form is not to get an answer. We have machines that do that for us. The purpose of graphing in polar form is that it teaches you to analyze how do changes in one variable affect another variable, because that's how scientists and engineers think. And if you're in trigonometry at this high level, that's how you're expected to think. So what you see on the screen, while true, is something that I don't recommend you ever use. Here's my general idea. You don't need formulas if all you're going to do is analyze what happens to r as theta changes. Because if you're willing to do that, and then you ask yourself how do these changes affect the shape of the graph, then you don't need any formulas, you don't need to memorize anything. In fact, this general concept will take us beyond limacons into any polar function that we want to graph. You won't have to memorize any formulas or any weird rules like if I have a sine, the pretzel is up or down, because you'll have a general strategy and you'll be able to analyze how changes in one variable affect other variables. And that completes the third of the 8 videos in this series.